Hello there, my name is Paul Meyer, and I am a second-year chemical engineering graduate student from the University of Texas at Austin, who works under the direction of both Dr. Nathaniel Lind and Dr. Grant Wilson. Today I'd like to talk a little bit about the crystallization of polymers to better explain what has been taking place in our other videos on our YouTube channel, where we freeze liquid nitrogen and simply smash things on the ground. Before I get into too many details, I'd like to first give you a little bit of background information so things are a little bit easier to understand. First, we should start off with the question, what is temperature? Well, we're all very familiar with a qualitative sense of temperature, that ice goes from liquid to solid at the freezing point of water, which is 0 degrees Celsius. And that higher temperatures generally correspond to things melting and becoming more easily deformed. To be more scientific, though, temperature is actually a measurement of the average kinetic energy of atoms and molecules in whatever you're working with. So kinetic energy is simply the energy related to things moving around at some velocity or speed. So the higher temperature, the faster things move around. You can imagine water molecules that are at its boiling point, for example, while you're cooking and you're boiling a pot of water. Those molecules are moving around more like a fighter jet, so they're going around very fast enough to be boiled off, while the water molecules in your freezer, those move more around like a turtle. So they're moving very, very slowly and don't really deform at all. So in our video, we show liquid nitrogen, and I don't think the video really showcases how cold liquid nitrogen really is. After all, we are taking a compound that you and me are literally breathing as we sit here at this moment, and we're liquefying it. So here's a few pictures on some cold things to give you a sense for how fast they're moving or how cold it really is. Room temperature that you're sitting in probably right now is about 70 degrees Fahrenheit or 25 degrees Celsius. Ice in your freezer is about 0 degrees Celsius or 32 degrees Fahrenheit. Now the South Pole we know is very, very cold. Here's a picture shown with a bunch of piles of snow. And it gets to be about negative 30 degrees in the summertime on average and about negative 60 degrees Celsius in the wintertime. The coldest ambient air temperature, according to a quick internet search, was on the order of negative 90 degrees Celsius. Now, keep all those things in mind. The coldest thing that was ever recorded in the air due to weather was about negative 90 degrees Celsius. Liquid nitrogen, on the other hand, is negative 196 degrees Celsius, or colder than that. That's the maximum temperature that liquid nitrogen needs to be. Liquid nitrogen is so cold that it pulls water out of the air and condenses it down, making the air look cloudy in our videos. So there's a very good reason as to why we're wearing gloves and using tongs in our videos, because you can actually get frostbite very easily if you come into contact with liquid nitrogen for too long. Now that we know how cold liquid nitrogen is, what does this have to do with things smashing on the ground? Well, normally when we interact with polymers, they're typically very stretchy or bendable or bouncy even. In our video, we show a racquetball, which is basically a thick piece of rubber or a type of polymer, and you hit this thing around like a tennis ball. So it's very bouncy, it's very easy to hit against a wall and have it bounce back like you would expect it to. Now, in the video that I'm going to show after, we're going to show you that normally at room temperature it bounces around like you expect, but whenever we put it into liquid nitrogen, it rapidly cools down to that negative 196 degrees Celsius I talked about. At this temperature, it turns into more of a crystalline material, where it shatters just like glass. The reason why it does this is that the polymer molecules, as shown by this cartoon, can be thought of like wiggling strands of atoms all strongly connected together. At room temperature, the racquetball is free to wiggle around quite a bit and is elastic enough to absorb the impact of us throwing it against the ground or against a wall or something like that. Now, I do want to mention that there are some attractive forces between these polymer molecules, but at room temperature, they're really not that significant because the polymer molecules, you can think of them, they're moving around so fast that these attractive forces really don't matter to them very much at all. So These attractive forces are much less significant than their wiggling energy, as you might think of it. Now, as the ball cools down, the polymers will wiggle less and less, and those attractive forces I mentioned become more and more significant. At some point, the polymer chains aren't really moving that much at all, and those attractive forces become the dominant forces. This is the point in which the polymer becomes much more crystalline, and as a result, its physical properties have changed quite a bit. Because it's crystalline, it acts more like a glass, and a glass is a great example of a crystalline structure. So, because the polymer has become crystalline, it broke, like glass, a crystalline structure. This is why the racquetball exploded so violently, because we were essentially throwing a ball of glass against the ground.
Hi, my name is Zhang, and what am I supposed to say? Hi, my name is Zhang, and I'm an undergraduate working in the Lynn group with Paul.
That's me. And today we are going to smash racquetballs using liquid nitrogen as described by the previous part of this video. So today with me I have Diana, who already introduced herself, and we're going to showcase how cooling things down very, very, very cold will make them act more like a glassy substance instead of a bouncy substance like a normal racquetball. So what I'm going to do is awkwardly place this down and have Diana, my assistant today, show you what a racquetball usually does. So, okay.
Really bouncy.
Very, very bouncy. So, on the other hand, we have this racquetball that's been sitting in liquid nitrogen for a little while. I'm going to wear a face shield and these gloves to make sure that I don't get frostbite or smash myself in the face with little shards of this now glassy polymer.
That worked.
So today we've learned a few things about polymers and the effect temperature has on those polymers. We saw that kinetic energy is used as a measurement for how fast those molecules are moving or wiggling about, and we saw how different interactions in those molecules can change the mechanical behavior of the polymer. Thank you all for listening. This has been Paul Meyer from the Lynn Group at the University of Texas at Austin, and I hope you enjoyed this video.